Thank you for inviting me. So today I'm going to talk about noise-based approaches in operational seismic hazard applications. And I will going to show you an example of site effect assessment in the French Rhône Valley. So of course this is done in collaboration with many people. So most of them are listed here. So some of them are in the room. Loïc, Gisèle Brèche, François Lavoué, Pierre Bouet, Laurent, Stélie. I think this is it for people who are here. Okay. So first, I would like to introduce IRSN. So I'm a seismologist at IRSN. So IRSN is Institut de Radioprotection et de Sûreté Nucléaire in French. So this is a French public institute in nuclear and radiation risks. So we have basically two missions. The first one is a public service missions. So we have to provide technical and operational support and assistance to public authorities regarding the nuclear and radiation risk. And to do so, we define and conduct research programs aimed at maintaining and developing the skills necessary for our expertise missions. So here is a simple sketch just to give you an idea of the landscape and the main stakeholders in the safety world, in nuclear world. So basically the nuclear operators here need to provide some safety studies, because they are in charge of the safety of their sites, to the public authorities. And the public authority ask IRSN for technical expertise on these safety studies. So we are here and we give some technical review of the safety studies provided by the nuclear operator. That's our public service missions, this support. And we are conducting research programs in relation. So as the IRSN covers all the nuclear and radiation risks, it covers a wide range of topics. So we have physicists, biologists, chemists, medical people, veterinary, a wide range of, and human science researchers as well, to cover all the broad range of risk. And there is a small team, quite a small team, 11 people, geologists and seismologists working on the seismic hazard. So this slide is to give you an idea of the presentation and maybe a bit also my job in the IRSN seismic hazard team. The idea is to try to make a bond between these two aspects. So on one hand, you have a methodology. So we are talking about this for the last days, for the last 3 days, about the noise-based approaches and the so-called noise correlation approach to give information about the Earth's structure. And on the other hand, we have at IRSN and in my job, my research, specific context, because we have to perform research studies in order to provide some seismic hazard assessment. So I may call it SHA for the following, but seismic hazard assessment. So it's a technical context because we need operational, quite easy to implement methodology. We need to provide input also for structural engineers so that it's give us some constraints also. The frequency content may be a bit different. We are working for French nuclear facilities, so metropolitan France, so a specific seismicity context. And this is guided by regulation, so a legal framework that provide further constraints. The idea is to make a kind of bond between these two worlds, and just to come back to the discussion about the interest of studying Mars and or the Alps, or just to say that from a practitioner point of view, we cannot do a fundamental research, but we need people who work on this aspect to try to really understand the theory, the physical processes on different type of objects, and then we have to convey fundamental research into practitioner applications. So it's a kind of collaboration work between academic work and fundamental research and practitioners. So this is really, really important collaboration. So the seismic motion is recorded at the surface. So it comes from the seismic waves that are generated by a seismic source, and these are modified during the propagation and to the from the source to the site and by the very local site configuration. So this is a usual way to decompose the different factors that influence the ground motion recorded at the surface using these three factors. And in practice, in SHA, these factors are transposed into three terms in what we call ground motion prediction equations, or GMPs, that are models or equations that are based on global data sets, and that provide a statistical estimate of the expected ground motion from very simple parameters, the magnitude, the distance, to describe the factors that influence the ground motion. So this is basically the idea. So here, in this talk, I'm focusing on the very last part of the propagation, what we call the influence of the very local geology, and what we call the so-called site effects, which comprise all the processes and modification of the seismic ground motion caused by surface geology and or local stratigraphy. And this site effects may be particularly strong in the case of complex geological structures such as sedimentary basin, as sketched here, where we may observe some seismic wave trapping that will lead to an amplification of the seismic waves and an increase in the duration. So this will increase the solicitation on buildings and structure. So in practice, this is often quantified, the site effect, by looking at estimating the amplification of the ground motion between the ground motion recorded at a site located on the complex geological structure compared to the ground motion recorded, what we call a reference station outside of this complex geological structure, and that is free of this influence. So how to take into account site effects in SHA, donc seismic hazard assessment? So there are different approaches. They are just showing two n-member approaches. So if you come back to the ground motion prediction equations, you may also you describe the source as with the magnitude parameters and the distance. You can also describe the site effect, the soil condition, by very simple proxies that will define the condition at a specific site. So one of them is the most commonly used is a VS30, that is the average shear wave velocity in the upper 30 meters. Another one is resonance frequency. So very simple parameters, but these simple proxies cannot catch the whole complexity of the site effect, especially in the case of complex geological structure. So there is another kind of approach we call site-specific approaches, which try to describe more accurately and with a more complete manner all the side effects, to characterize the side effects and to understand the physical processes behind. So basically, you can use this site-specific characterization of your side effect and plug this characterization to the ground motion predicted by GMP at the reference station, at a site that is free of this. So you will compute your ground motion at the reference using a GMP, because you cannot do much better at this time. And then you will plug something which is really specific to your site to complete the ground motion predicted at your site. There are different, basically two main approaches in site-specific approach. One is the empirical estimation that is based on the direct characterization of the site effect through seismic observations. And the other one is a numerical modeling of the site response. This is based on the modelization of the ground motion using the numerical simulation of wave propagation in a model of a soil medium. So here I'm showing a slide to give you the context and the scientific issues in our study here. So our target zone here is a widespread Tricastin nuclear site, which is located in the French Rhône Valley in southeast France here. And this site, this nuclear site, is located on the deep and elongated canyon, Rhône Canyon, that was dug during the Messinian salinity crisis 6 million years ago. So the Rhône at this time, the Rhône River dug a deep canyon into very hard Cretaceous sandstone and limestones. And here is a picture of the Vikos Canyon in Greece, which has pretty much the same scale than what the Rhône Messinian Canyon looked like at the Messinian time. So it gives you an idea of what was the landscape at the Messinian time in the Rhône Valley. And so this canyon is now filled with Pliocene and Quaternary much looser sediments. And so the strong material contrast between the sedimentary filling and the substratum and the expected confined geometry make this geological structure prone to site effects. But at the time of when we started this project, the geological structure was poorly known. We have some very local characterization, but we don't have a global picture of the geological structure, and we will see that it is important to get this scale. And even if the sketch does not reflect this, this area is a quite heavily industrialized area with some critical infrastructure, and including a nuclear site. And of course, this there is a need for a robust seismic hazard assessment studies, and including the studies of the influence of this geological structure. But we are in metropolitan France with a low to moderate seismicity context, and the site-specific studies have historically been considered as difficult to carry out in such a context because of the long return period of moderate to large earthquakes. So you see me coming, saying that maybe in this context the ambient noise may be of great interest. The last issue it's that we are in a noisy industrial area and so noisy environment. So how, to what extent the seismic observation it challenges, it's a bit challenging about the quality and do we have exploitable observations. So in this context, in order to characterize the Messinian Rhone Paleo Canyon and the impact on the seismic motion, we launched the French-German DARE project. DARE is for dense array for seismic site effect estimation. So the idea is to use dense seismic arrays for the estimation of site effects in low to moderate seismicity region, and this is an application to the Rhone Messinian Canyon. So this is funded by IRSN for one acquisition, and both French and German research agencies, so ANR and DFG, at the same level of amount, and this started in 2020 and it will end at the end of 2023. There are 4 partners involved, IRSN and UGA for the French part, and the University of Potsdam and GFZ for the German part. Okay, so the seismic data are really at the heart of this project. So this is the same message than Anne. We need to go and acquire some data. So this is maybe obvious. This is not completely in operational and industrial discussions, because sometimes you hear that okay, but I don't know what to do with the data and it will not be useful, so whatever. And say, so the idea is to say no. If you go and acquire some data, you can do something even in this area. Even so, that's basically the idea. So we hope that it will be successful, but this was the idea, at least at the beginning. So we acquired two different data sets, complementary data sets between 2020 and 2021. So the first one is dense 400 node deployment, 3-component nodes. And we deployed them for 1 month, and so the target was to record the seismic noise. And to complement this first acquisition, we deployed 50 broadband stations, the same target area. So I did not mention, but here is about 10 kilometers, so we kept the broadband were on field for more than 8 months, and the idea was to get some seismicity and to record some seismicity. So different temporal and spatial scales and 2 different targets regarding the seismic data. The 2 data sets will be distributed by RESIF and Geophone, so the French and German data center. They will be in free access at the end of 2023. In the meantime, if you have a specific interest in working on this data set, you can contact me. We have DOI also for these 2 data sets. Okay, so a few months before this, the first massive deployment, the 400 nodes, occurred the Le Teil earthquake of magnitude 4.9, 20 kilometers north of our target zone, so here on La Rouvière fault. So it severely damaged the villages in the vicinity of the surface rupture, and it was the strongest earthquake in metropolitan France since 1967. So it was a kind of an event for us. And it's was a good way to illustrate the site effect in our target zone, because we had some station installed at that time. So here the triangle showed 3 broadband stations. So one located at the Jurgonian limestone, so very hard limestone, and 2 were located on on top of the canyon, sedimentary canyon. And here are the recordings of the Le Teil earthquake. So you see that for the 3 components. So you see the very big difference between the recording at the reference rock station and on top of the sedimentary canyon with a much larger amplitude and a longer duration. So this is just an illustration of this, the influence of the structural canyon on the seismic motion. So, so the project was funded before that, but it was still support the idea of the importance of characterizing this aspect in the area. We also had 30 nodes installed at that time, because we at that time we were performing a preliminary noise test for the 400 node deployment. The bad thing is that the recording were clipped, so preventing usual analysis of the ground motion. Okay, so here I'm gonna show the different approach we use in the DARE project. So we use the 2 approaches in the idea of getting a kind of robust and extensive study of the site effects in the area. And regarding the empirical estimation, we will use both the seismicity and the seismic noise. So I will start with the numerical approach and what we are doing in the project, what we have done so far and what we are doing to characterize the medium, the first step. So we are applying complementary approaches. So I agree with you that we need complementary approaches to get confident in our results. So, sorry, the first one was to use the ambient noise surface wave tomography. So we have also discussed this. So we did that with SysProbe, which is a company specialized in the processing of such passive recordings and passive imaging, and even monitoring, but here's the imaging. And so the idea is the same that what Laurent and Anne presented about the noise-based imaging, but for the Alps, we were looking at the lithospheric scale. Here, we are looking at a very tiny scale compared to the Alps, and we are interested in the first kilometers and even the 500 meters, maybe. So it's the same kind of methodology, but at much smaller scale. And so not the same frequency content, and so different challenges between the two aspects. So here is a basic workflow. Sorry, this is in French, but I just extracted from the SysProbe. It's a SysProbe workflow. So basically what you did, we computed, they computed all the noise correlation function between all the pair of stations, so more than 80,000 pair of stations. And we can first derive the measures, the peak, the group velocity dispersion curves on each for each station pair that is shown here, and then you can regionalize and invert to get a group velocity map at each frequency. So this is for the group velocity. In the SysProbe workflow, usually they also use an array-based approach to get a 1D average phase velocity over the whole network. In our case, because the medium is really heterogeneous, it didn't make any sense to have a 1D average phase velocity for the whole network. So the idea here is to perform a clustering of the group velocity dispersion curves to try to discriminate different behaviors in the area, in the data, the dispersion curves. And here is what has been revealed. So we have 3 clusters, so 3 main domains that are very consistent with the expected geology. Here, with this cluster related to the Yurgonian limestones. Here, the blue ones, the upper Cretaceous, corresponding to the upper Cretaceous formations, and the red one to the sedimentary filling. So this was a nice result to see that this clustering leads to a result in group velocity that really match the geology, the 3 major units in geology in our area. And then we can use these different information, phase velocity, group velocity for Love and Rayleigh waves to get a 3D VS model in the area. So here I plot just two sections, north-south and east-west. So just it's worth noting that here the color scale has been chosen to really distinguish between the sedimentary filling and the substratum, so it may be a bit misleading, but we clearly observe a difference and the imprint of the canyon. And another representation is the isovelocity contour of VS equal 1,200 meters per second. That has been found to be a good indicator of the transition between the sedimentary filling and the substratum. And if you look at the map of this, the depth of this isovelocity, you observe this, and this is it also be good agreement with the what we expect in terms of geology, with the imprint of the Rhone Paleo Canyon here in the eastern part of the valley, deepening southward. And here we have also the imprint of the Paleo Canyon of the Ardèche River, which is a tributary of the Rhone. So we have these two signature in our VS model. To complement the VS model, we also try to build a geological or structural model in the area. So I'm not an expert in that, but we are working with a geologist colleague, Mark Cushing, who is in charge of this in the project. So so this is a work done by during a master internship of Nadaba Bagayoko last summer. So she used different observation, different data, so surface geology data from the geological map and several field survey. Borehole database information we have in the area, and she also reinterpreted some seismic reflection profiles here that were acquired in 2008 by NG. So she worked on all this. So this is an example of this work. So she reinterpreted this seismic profile. She put some constraint using the borehole, and she went on field to see if it makes sense to work on this data. And so to build this geological structure model. So here is the topography of the canyon bottom. So geologists call this the Messinian erosion surface, and seismologists say the canyon bottom. So, but it is basically the same. So you have the topography of this interface here, shown here. And you see that it is in the big picture in good agreement with what we have seen in the VS model with the imprint of the Paleo Canyon here, the Ardèche Canyon here. And we have a 3D printer close to our lab, so we had fun printing our Messinian Canyon. And the last thing we've tried to as an imaging approach is to use the so-called H/V spectral ratio method. That is a very commonly. That's a picture of you? No, it's 2.4, maybe. So Messinian Canyon and Mars, maybe. So yeah, so this is a very commonly used method in operational context because of its easiness of implementation. It's a single station. So we wanted to perform this to see the performance and compare to the other approach. And basically the idea, is that we can, from this H/V curves, we can very simply extract the fundamental resonance frequency of local stratigraphy by just picking the frequency of the peak in H/V. And using a 1D assumption, you can relate this resonance frequency to the velocity of the layer above the impedance contrast that is leading to the resonance, and to H is the depth of this interface. So you have this kind of relation you can use. So that's what we did. So we picked, we take all of our 400 data, and we pick the resonance frequency, and by using our velocity model, we transferred, we change in the depth, so to map what we expect to be the main impedance contrast. So here is the map we obtained. So once again, there is a good correlation for the at first order. Now we'll come back to the comparison just here. So we tried the first comparison between the different approaches. So as I said, the first order, the good agreement, the overall geological structure. It differs. It mainly differs in this area, in the transition between the two canyons. So there's not surprising that there are also some differences, because the different approaches are based on different assumptions, different observation, or different physical properties of the seismic waves. Here we have geological interfaces. Here we have a velocity model, so the interface will be expressed as a VS contrast, but if you have different geological layers with the same velocity, you will not see any interface. So here, the main difference in the transition in this area, it's here you see a kind of gently dipping surface toward the southeast, and it is really consistent with what we expect for the Jurgonian. You cannot see anything, but the Jurgonian layers at the regional scale that is dipping toward the southeast. So this surface here is interpreted as the top of the Jurgonian limestones. But in this area, you see that it does not map the same interface, but a much shallower interface, because the Jurgonian limestone continue to go the same way. But so we jump and map this area. this is just because you made some assumptions in picking your resonance frequency, and in complex geological mediums such as this one, you may have several interfaces and several impedance contrast, and if you pick different frequencies, you will pick different interfaces causing the different resonance. But it may be seen here as first interpretation is to say that we mapping the main impedance contrast, but not a unique and continuous geological interface. But this may also be seen as the key features in terms of seismic site response, the main impedance contrast. So the comparison here raised the question of the nature of the dominant interface in terms of seismic site response. Is it the top of the Yorgonian limestone, or this just the bottom of the canyon, or so what is the nature of the main interface and its continuity throughout the target zone? So this will be addressed through a numerical simulation in the following. Okay, wow. Okay, so we also characterize the attenuation, so very first characterization, so by using array approaches, the methodology proposed by Prieto in 2009. This is a work by Marco Pils at GFZ. So we can get some 1D profile for different sub-arrays, here giving an idea of the QS at depth for this different part of the network. So this is ongoing, but we have some first constraint, I would say. I'm going to go a bit faster because I'm late. Okay, so we have this first constraint that will help us, even if it's not a refine at this stage. We are not it's an apparent attenuation. We have some 1D. We need to go toward a 3D estimation, but at least we have some first constraint to put on numerical simulation as well. Okay. So now that we have some characterization, so it's still ongoing work, but you've seen the idea of what we have so far. The idea is to put in numerical simulation. So the question is to build a representative 3D model from the different observation we've got. So we have a different type of data observation, different resolution. So how to combine everything into a single 3D model for numerical simulation. So this is the work by François Lavoué. It is not obvious to do this. So his idea was to try to test a different implementation and see the sensitivity of the result to the implementation and to different parameters. So far, he has tested two n-member models, a blocky model and a tomographic model, and you will see he will first see the first the comparison in these two models. So okay, so I will skip the movie maybe. Just this is one of the first simulation we got last week or so. So just to visualize the trapping of the waves in the sedimentary basin. François has a poster, so we'll talk. You can stop by and you know better. So the conclusion about the numerical approach. We have first a 3D site characterization. So it needs it's ongoing, but we have this first information. And as I said before, at the beginning of the project, we had nothing. So this is already good news. We need to define a strategy. The numerical are in progress, and we will have to come back and see the interest of using the ambient noise in such applications. So the first thing is that we have a way to get a 3D VS model that was not possible some years ago. So that's the first thing. We need to improve the VS model, especially in an area with very strong lateral contrast, where we know that the first model has some limitation. We are working with François, Pierre, and Laurent to see how we can improve this first model. And for side effect assessment, precisely, we will be investigated the interest of using such a smooth model through numerical simulation. Okay, I have to skip to the empirical estimation, so very fast. So the idea is to do using both seismicity and seismic noise. Do we have enough seismicity? Is the seismic noise usable to estimate the site effects and the comparison? The idea of the comparison is to provide a condition of application of seismic noise. Can it be used as a blind tool to predict site effects in the future? That's the idea. For the seismic noise, I'm going to skip this because this is a work by Loïc, and Loïc has a poster, so he will do the job. So we have some first idea of some first methodology proposed to estimate the amplification using the noise, and we are seeing noise-based amplification map in. So these approaches are coming into operational aspects. So we need to really understand the conditions of applications of such methodologies. So this is the idea of the work by Loïc. So here's the poster, so I invite you to stop by. No, this one I want to show it. So this is a movie by Pierre. So the idea is going further, not doing the raw noise, but the noise correlation function to try to extract some information. So here you are seeing the amplitude. It's a movie tracking the amplitude of the noise correlation function between the node that was placed on Larouvière fault and all the other nodes. So this mimics the wave field generated by a virtual source on Larouvière fault, basically. So you see that there are some fluctuation in the amplitude before the arrival, the first arrival. And you're going to see the wavefront of the surface waves here. And you see, so you have to wait a little bit. Here you see a distortion linked to the slower propagation in the Rhône Paleo Canyon here. It's really clear. And when the surface waves, you see higher amplitude remain in the eastern part of the valley that corresponds to the Paleo Canyon as well. So the idea of this first movie is that the noise correlation function catch the signature of the site effect at first order. So we want to exploit also the noise correlation function to characterize the amplification, the amplitude, and the increase in duration and the complex propagation within the medium. And the seismicity, just we are analyzing the seismicity. So it was a hard job done by Catherine Hanman, who was a postdoc at University of Potsdam, and now she got a position. But she analyzed the data set at this rock station here, more than 8 months, and to build a catalog, a first catalog of seismicity. And she selected 400, more than 400 events, more than earthquakes. with a quite good azimuthal distribution and a quite good distribution in distance also. So we have this this first catalog. We would like to improve using other approaches, AI approaches, maybe to build to complement this first catalog. And this is an example of the first amplification estimated using this event. So this is done with for a bunch of earthquakes. So here is the amplification. Sorry, where am I? Yeah. So here is the amplification plotted as a function of the frequency for all the stations of our network related to this reference workstations. So what can you see here? That for some station in the basin you have, and for some frequency you have an amplification of 8, and it remains it's a quite broadband. And we also the thing that we can observe that there is a large variability within the network. Some stations are we can observe an amplification of 2 maybe, and some it's 8. So you have the continuum of amplification over this network. So this highlights the importance of understanding at this scale, because we have a strong and very fast spatial variability from one station to the other one that probably reflects the complexity in the medium and the 3D geological structure, and then you can map at the different frequencies. Okay, so I will just skip. Cannot skip. Okay, so the idea is to compare the numerical simulation, the noise-based amplitude. I got, okay, yes. For example, here is the first map of amplification you get from numerical amplification, noise-based and seismicity-based, and we will try to combine everything to get a robust estimation. And a work package that is going to start is to use this site-specific extensive study to test the performance and the conservatism of much simpler approaches commonly used in SHA or paraseismic code. This is going to start, and this will be done by our colleague at GFZ mainly. Okay, thank you very much. And the field, because we spent quite some time on field these last 2 years.